Okay, students, we're going to start into chapter 11. Huge chapter. There's a ton of information in here. It's all about circles. It's going to be a lot of material that's covered. The first thing that I would like for you to do is I'd like you to do this opening proof. So if you want to jot down off to the side, I have 8 steps. It's not super hard, I hope, but maybe pause this for a moment right now and go ahead and give this a try. Okay. Now, I'm going to talk through this proof quickly. If you want to look at the full version, it'll be on this on the solution document in the regular spot. But if you're going to prove this, we can draw on radii, of course, and those radii are congruent. We're also given perpendicularity, and of course, we have this reflexive piece in the middle. So those two triangles are going to be congruent by RHL, and that's going to lead to AP being congruent to PB by CP/CTC. Now, if those are congruent, that of course means that OP bisects AB. So, not a hard proof. Again, it does end up being 8 steps, but you can look at those in the solution document. Now, why did we spend time looking at this? It's because it leads to a new theorem. And down here, what that theorem is going to be is if a radius is perpendicular to a chord, having some trouble with my pen here, then it bisects the chord. Okay, now a couple things to clarify there. First of all, a chord is just any segment that connects 2 points on a circle. So in this case, AB is the chord, okay? Diameter would be a special chord. Now, I know here that it says if a radius is perpendicular to a chord, and OP is not a radius, but we could extend OP to make it into a radius. Okay, the extension isn't shown there. But what we were given perpendicularity. If a radius is perpendicular to a chord, then it bisects the chord. Turns out the converse is true as well. And that would be what? If a radius bisects a chord, that is not a diameter, then it is perpendicular to the chord. Okay. That's the converse of the first one. Now, there's one more theorem. Doesn't come up as often. The perpendicular bisector of a chord passes through the circle's center. All right, so it's 3 new theorems, and we're not going to do a lot in proofs with them, but we're certainly going to be applying them with problems regularly. We'll get to those problems in a little bit. Okay, down here, I'm not going to go through all this stuff. A lot of these definitions you already know, and you can obviously refresh your memory by looking in section 11.1 in your textbook. I'm going to go over some of the key points though. So circle, center, radius. A circle, by the way, a circle just refers to the ring, okay? Not the interior. The interior is called the interior of a circle. This, of course, is the exterior, but the circle itself is just the ring. The circle is not defined as a disc, so to speak. Okay, an arc, I think that's pretty self-explanatory. It would follow the path of the circle. So if I call those points A and B, that would be arc AB. Okay, and we use that little hook symbol on the top. Now, this is called a minor arc. A minor arc is a short way around, all right? It means it would be less than 180 degrees, okay? The major arc would be the long way around. So if you wanted to go this way, you would say major arc AB. Or you could put a point in here and call it arc ACB. Okay, that means you're going the long way around. So these are both ways of showing going the long way around. This is the short way. If it doesn't specify major or minor, you're always assuming minor, right? Always assuming minor, always assuming the short way. Concentric circles are circles with the same center. Interior, exterior is pretty straightforward. Chord, I talked about that earlier. Chord is a segment. Again, we got pen problems here. Not too sure what's going on with that. It is a segment connecting 2 points on a circle. All right. Now, distance from a center to a chord, of course, whenever you're measuring from a point to a segment, you always measure the shortest way, so that would be the perpendicular distance. Diameter, of course, is a special chord. It's a chord that passes through the circle's center. It's the longest chord possible for a particular circle. Okay, the next thing, my dot there is back. Next thing is a sector. So a sector is a portion of the circle and its interior. So if I call this D, E, F, sector is like a piece of pie, okay? It's the area bounded by D, E, and F. It's made up of an arc, in this case, arc EF, and 2 radii. Okay, that's a sector. Obviously, a sector could be very big, could be very small. It's a portion of the circle, though, fraction of the circle. Area of the circle, I certainly hope you know, is pi r squared. Circumference would be 2 pi r. Some students have learned that as pi d. Of course, pi d, pi times the diameter is the same thing. Usually we like to use radius, though. All right. Okay. Next page gets into some problems. I'm going to do some of them you can do on your own, and you can follow up with the solution document yourself. Here, we're given that the circumference is 24 pi. And don't hesitate to pause at any time. You can try these things yourself and follow along with the instruction later. Circumference is 24 pi, so 24 pi equals 2 pi r. Whoops, wrong thing there. The pi's just cancel, and of course r would have to be 12. So you have a radius of 12. Now, something that you're often going to do in a problem like this is you're going to drop in an altitude. Remember, that's perpendicular. That could be extended to be a radius, and any radius that's perpendicular to a chord is also going to bisect the chord. So that means that these two triangles are going to end up being congruent. And if the whole original angle is 106, this would have to be 53. Okay. Now, this is a problem where you would have to use trig. Okay. Whenever you get this angle that's a little bit weird, not 30, 60, 90, not 45, 45, 90, we might have to use trig. Not hard to do. Sine of 53 equals x over 12, and x ends up being, I think it comes out to 9.58. Now remember, it's asking for the chord, the length of the chord, so we'd have to double that. Now I'm not gonna, this was a rounded version, if I double it, AB ends up being 19.17. Now this thing here is often, when it says rounded to the nearest hundredth, that's a kind of a giveaway that you might have to use trig. Not always, but when you see that, one thing that should be going through your head should be, hey, I might have to use trig. Okay. Here in this one, in a diameter circle with a diameter of 40, go ahead and draw in a chord. Now, a lot of times, where do you want to? I'm not even going to draw in the diameter. I get that because the radius is 20, and I want to create a triangle. I'm going to create a right triangle. Okay. Now, the distance from the center of the to a chord is 24. I'm sorry, find the distance from the center to the chord. The chord length is 24. So if the chord length is 24, that means this altitude cut that chord in half, and you have 20, 12. This is actually a triple. Okay. And this x ends up being 16. Okay. That's just a 3, 4, 5 triangle multiplied by 4. But creating this kind of diagram with a drawing in a radius and creating a right triangle is huge. I'm not going to do the next one. You can check the other the document for that. You are going to have to use trig here. Okay, I will tell you that. Now I'll give you the answer is 106.26. Create your triangle like we did earlier. This is a harder problem down here for sure. And it's not simple. If you want to pause and try to do this yourself, that wouldn't be a bad idea. But if you get stuck, it is kind of tricky. Okay, so it says they have a common chord. The centers of the circles are here and here. Okay. And, usually when you have a circle, drawing in a radius is a good thing. So I'm going to draw in a radius of the bigger circle. I'm going to draw in a radius of the smaller circle. Now, it told us that those radii were 13 and 15. Now, this one's a little bit weird. Okay, I mean, it's a tougher problem for sure. And what I'm going to do here is I'm going to go ahead and call this, remember, it says the distance between their centers is 14, right? So this length here is 14. We know that this whole length from here all the way to here is 15. So this little piece, I'm going to extend this. That has to be 1. Okay? Because that's a radius. Now, I know this whole thing's 14, but it's been cut into pieces. So I'm going to call this x, and I'm going to call this 14 minus x. Now, remember, I hope you realize I'm going to call this y. This is going to be perpendicular, okay? I created this triangle up here. I could have also created the triangle down here, okay? And these two big triangles would be, we've talked about this before, these two big triangles would be congruent by SSS. That would lead to like this little angle being congruent to that little angle, and then you can prove this small triangle congruent to its twin down there. That would force these two angles here to be both congruent and supplementary, so they are a right angle. Actually, anytime you have intersecting circles like this, the line connecting the centers, okay, the line connecting the centers is always going to be the perpendicular bisector of the common chord. All right. Now this problem here, now we can set up. This is not the easiest thing. We can set up a little system. We got a little Pythagorean theorem, right? Look at the triangle on the left. The hypotenuse squared equals leg squared plus other leg squared. And then I have the same thing with this little tiny right triangle. 169 equals y squared plus x squared. Now I'm going to expand that. I'm sure none of you are going to make a mistake doing that. I'm going to 225 equals y squared plus, this would be what? 196 minus 28x plus x squared. Nothing changed down here. I'm going to take these two equations. I'm going to subtract them. That means this would go away. And you know what's pretty sweet is that goes away too. 225 minus 169 is 56. And you get 196 minus 28x. And if you move that over and solve for x, you will get x equals 5. Okay. If x is 5, you can do a little Pythagorean theorem. Actually, it's a triple, right? That means y is 12. So you were asked for the common chord. The chord would be 24. That's a tougher one for sure. Might have to replay that. Okay. Now, these last two, I think what I'm going to do, I'm going to leave those for you. I highly recommend that you do them both. I think that they're good practice problems. Okay. My screen will come back here. These will be posted to Canvas. Actually, let me talk through this top one. All right. Remember, a common theme here is drawing in an altitude, and that creates a bisector. It says PQ is 4, RQ is 10. So this altitude will cut that into 5 and 5. And then it says that PO is 15. We have to find PS. Actually, ends up not being too bad. This is not drawing a scale at all. So we got this skinny right triangle. This is 9, this is 15. That's a triple. So that means, even though it doesn't look like it, this piece in here, it's going to be 12. Okay, you got a 9, 12, 15 triangle, 3, 4, 5 times 3. Now look over here. That's 5, this is 12. That means RQ must be 13 from the triples. And RO is 13. That means the radius of the circle is 13. So this piece is 13. So that means PS, the little piece sticking out here, must be 2. So hopefully that helps. And, please definitely try this last one. This last one's a good one. And check the solutions, rewatch any parts as necessary.